We are back. This is Dr. Jenkins. This is part 2 of the chapter on fuel sources and energy metabolism. You may recall at the beginning of this chapter, we talked about the structure of skeletal muscle. We talked about how the myofilaments slide past each other to enable contraction, and those myofilaments were actin and myosin. And then we talked about when we have glucose that's going to be used as fuel, there's actually another step. The muscles cannot utilize glucose directly. Instead, we've got to convert that glucose into ATP. Does this sound familiar, folks? Because it is ATP that is the usable energy source. All right, so our next question, as I introduced before, is to talk about, well, how do we convert that glucose into the usable energy source of ATP? And we do it through these 3 chemical pathways. Now, if you've heard about cellular respiration, which is the overall term for these 3 pathways, it can get really complicated. The good news is that we're not going to get very complicated. I would just like you to know some very basics. So here we go. To start, you're going to be able to identify that these are the 3 chemical energy pathways that happen in order for us to convert glucose into ATP. You can imagine an exam question where I have these listed in order, or I have these listed, and I have you put them in order. The first series of chemical reactions that must happen are something called the intramuscular high energy phosphates. That happens first. Then we move on to another series of chemical reactions called anaerobic metabolism. And we finally move into our final set of chemical reactions called aerobic metabolism. So these series of chemical reactions occur in this order. Be able to put them in order. The first 2 are considered to be, The first 2 are considered to be anaerobic. So this one and this one are anaerobic. And all that means is, in order for these chemical reactions to happen, it does not require oxygen. So both of the first 2 are anaerobic. They don't need oxygen in order for those chemical reactions to take place. However, this third one is, as the name suggests, aerobic, which means that it requires oxygen. Let's talk about our first one, the intramuscular high-energy phosphates. Okay, as we said, this series of chemical reactions happens first. So it's the series of chemical reactions that happen first. We know that it's anaerobic. You don't have to know how. So don't worry about these specific steps. What I do want to point out, though, is that this first series of chemical reactions, the intramuscular high-energy phosphates, requires the use of something in our body called phosphocreatine. So be able to pair those together. This first series of chemical reactions requires something in our body called phosphocreatine. Our body has this naturally. Cool. I'm bringing this up because now we can understand something about one of the supplements that is commonly used called creatine. And what creatine does is it adds more of this to what our body already makes. And what it means is our muscle cells can produce a little bit more energy in this phase. We're going to come back and talk about creatine as a supplement later. but we're building the important building blocks. So I'd like you to just be able to pair phosphocreatine, something that our body naturally produces, as something that we utilize in this first series of chemical reactions as our cells are producing ATP. The last thing is, how long will this create energy for our muscle cells? And the answer is several seconds. Okay, so this is the first series of chemical reactions on the way to producing ATP. It is anaerobic. It utilizes something our body already makes called phosphocreatine, and it will give us ATP, just a little bit, that our muscles can utilize to provide contraction for only a couple of seconds. But because most of our physical activities last longer than a couple of seconds, we have to rely on a second pathway of chemical reactions to create more ATP. And our second series of chemical reactions is collectively known as anaerobic metabolism. We know that this does not require oxygen. And now I want to point out where it's happening. These chemical reactions are happening inside of the mitochondria of the cell. That's this little mustard color looking thing. The first phase happened in the cytosol outside of the cell, but now we're in the mitochondria. And if you think back to biology you've had before, when you talked about the parts of a cell, here's our animal cell, here's the nucleus, here's the endoplasmic reticulum, and so forth. There were these structures that kind of look like sausages called mitochondria. And the mitochondria of the cell produces energy. And now we're seeing how. This is where many of the chemical reactions occur to produce ATP. And then lastly, you should know how long this will provide energy for. An additional maybe 5 to 20 seconds. So let's review. Here we are in our second series of chemical reactions. It is also anaerobic, just like the first series of chemical reactions. The chemical reactions of this step are occurring in the mitochondria of the cell, and it produces enough energy to last maybe 5 to 20 seconds. But again, a lot of our physical activity lasts longer than 25 or 30 seconds. So we ultimately like to use our third and final series of chemical reactions called aerobic metabolism. We get more bang for our buck. I think I have to sneeze. Hold on. I knew it was coming. Pardon me. This series of chemical reactions occur last, only after we've done the first two in order. This series of chemical reactions is aerobic. It requires oxygen. It does involve these things, but you don't have to know those. So don't worry about that for now. This step provides the most ATP. That's why I have the stack of cash there. Even though it takes longer to get to these chemical reactions because we've got to wait for oxygen to be available, once we go through these chemical reactions, it's going to provide us with a ton of energy. Any type of activity lasting, 20 or 30 seconds plus, you're going to be dipping into this step to provide ATP. I do want to show you how fruitful this step is. For every one glucose molecule that enters it, we can yield a net of 36 ATP. So one glucose molecule goes in, and after we're done with these chemical reactions in this step, or series of steps, for every one glucose, we get 36 ATP. That is a huge yield. All right, so make sure you review the basics of what we just talked about. These are our 3 energy pathways for our muscle cells. We had the intramuscular high energy phosphate. That's what we're going to go to first. It is anaerobic and only gives us ATP for a few seconds of activity. But if we exercise for longer, we're going to continue on to another set of chemical reactions called anaerobic metabolism. It's also anaerobic. And this will give us activity for another, I think on the other slide I had 5 to 20 seconds. But if we exercise longer than, say, 30 seconds, we're going to be tapping into our 3rd series of chemical reactions called aerobic metabolism. This requires oxygen, and it gives us the most energy. For every one glucose, we get 36 ATP. Hopefully I've debunked the scariness of this. As I keep saying, and I will keep saying, you only have to study what it is we're talking about. What I circle, underline, and what it is I'm talking about. Now, you don't have to know any of this. This is just to give you some examples in terms of different sports and what types of energy systems we rely on. The anaerobic energy systems were steps 1 and 2, right? The high energy phosphate and the anaerobic metabolism. The aerobic energy systems was our 3rd energy system, the aerobic metabolism. The more endurance the event is, the more you rely on our aerobic fuel sources. The shorter the event, how long does a football play on average? You guys can tell me. 6 seconds maybe? The shorter the sport and the higher in intensity, we're going to be relying more on anaerobic because it gives us quick energy. We don't have time to wait around to get to that oxygen. You don't have to know these numbers. It's just some examples for you. Okay, now let's talk about glucose, glycogen, and fat. I know it can be a little confusing because we just spent time talking about how we produce ATP. So what I want to point out is the steps that we just talked about were how we convert those nutrients into ATP. And I know that I was talking mostly about glucose, but it can also be glycogen and fat. Okay? So what we just talked about was the chemical steps of how we convert those nutrients into the usable energy source, which is ATP. But now we're going to back up a little bit. And I want to talk about which nutrients we can use, because we can feed into this system glucose, right? We can convert glucose into ATP. We can also feed into this system glycogen. And we can also feed into this system fat. And actually, to a very small degree, even protein. But I want to talk about what's in blue. How do we know when our muscles is going to utilize glucose versus glycogen versus fat? We know ultimately all those nutrients have to be converted into ATP. And we just finished talking about how, whatever nutrient it is, how that gets turned into ATP. It occurs through those chemical steps, the high energy intramuscular phosphate, the anaerobic metabolism, and the aerobic metabolism. But now we're backing up. And I've actually put these in order. So our muscle cells will utilize the same order. Our muscle cells will always first feed glucose in. Because glucose is available in the bloodstream. It's right there. So when our muscles need energy, when the muscles cry out, yo, need energy, the first fuel source they're going to use is the glucose in the bloodstream because it's right there. Then, if those muscles keep crying out, need energy, I'm working out, need energy, that blood glucose may not be enough. So then, our muscle cells are going to be tapping into the glycogen or the stored glucose. Remember, glycogen is stored glucose. And here, I do want you to know where we store glucose. We have glycogen in our skeletal muscles, and we have glycogen in our liver. 2/3 of all of the glycogen we have is stored in our skeletal muscles. And then the remaining third of glycogen is stored in our liver. But this is perfect for the muscles. The muscles are crying out, need energy. So they're going to use the glucose in the bloodstream right there. But what if they need more energy? Then they can go right within the same muscle, right next door. They can get glycogen and break it back down into glucose. So glycogen would be what our muscle cells feed into the system second. And then what they would use third would be fat, the triglycerides. Make sure you know this order. Now, as I mentioned in the previous video, in our general principles of nutrition, we tend to be burning a mixture. I'm going to change colors because I want this to really pop. How about purple? Ooh, I like purple. We are pretty much always burning a mixture of all three of these. So if you exercise for 5 minutes, you go for a jog for 5 minutes, you're burning a glucose, glycogen, fat mixture. Your muscle cells are utilizing all of the above, which is a good thing. But it's still important that we understand the order with which our muscles utilize this fuel, because this can help us understand what athletes should be eating. For example, if you know that we utilize glucose and glycogen for the shorter durations first, maybe Usain Bolt, that 100-meter sprinter, he's going to be utilizing more glucose and glycogen, so he's going to need more sugar in his diet, a healthy sugar, and less fat, because he's not exercising long enough to get into much fat. Even though he might be burning a little bit of fat, it's not a whole lot. Where on the other hand, if you have an athlete that's more endurance, we know that we burn fat last in terms of what the muscles will activate. A marathon runner is actually going to need a decent amount of good fats in their diet because they're going to be utilizing more fat. So even though we're always burning a mixture, it's important to know the order with which our muscles activate this mixture, because it can help inform us of what different types of athletes should be ingesting. All right. So here is an example of what percentage of each. You do not have to know this table. I'm being crystal clear. But here we have our glucose, which we go to first. So I'm not sure why they had to use the same color but different shades. Kind of confusing. So the lighter one here is the glucose. So we're going to go to the glucose first. But look at how, as we get towards the higher duration, someone who exercises for 20 minutes or more, our amount of glucose contribution actually starts to go down. When I do the Ironman, which takes me an ungodly amount of hours, we're talking 13, 14 hours, I'm going to be utilizing a little bit less blood glucose. Now, let's use a different color, because I actually like this chart. Let's use purple. Purple is going to be our glycogen. Okay, let's do solid for glycogen. So here's our glycogen. Okay. Look down here. As we get a little higher in duration, we're actually going to be using less glycogen, but it's still a part of the mix. But let's look at fat, because I like that one even better. Let's make fat green. So fat is this one. Okay. Fat is an easy thing. As we increase the exercise duration, we're going to burn more fat. Okay. You don't need to know this chart. For those of you that like charts like me, I think it can be instructive, but there we go. All right, so putting it all together. And I really like this slide because I think it really puts it together. That's obviously why I did it. Haha. At the immediate onset of exercise, which energy system are we going to be utilizing? Because we always go to this one first. We're going to be utilizing intramuscular high energy phosphate. And what's our fuel going to be? Because we always go to glucose first. So if someone's doing a 5-second Olympic weight-lift, they're going to be utilizing, they may only need the intramuscular high energy phosphate and then only need to use glucose. Let's say we get to 15-second activity. Usain Bolt's 100-meter sprint just over 10 seconds. So he utilized the intramuscular high energy phosphate plus this energy system, the anaerobic metabolism. He used glucose, but now he's also using glycogen. And then let's go to a longer duration. Here we have a marathon runner, Eliud Kipchoge. He's the dude that just beat the sub-2-hour marathon mark. He utilized at the very onset the intramuscular high energy phosphates, then for a little bit the anaerobic metabolism. But because the duration is so much longer, he's going to be relying most on the aerobic metabolism. He's going to utilize glucose at first, then glycogen, but he's also going to be utilizing the most fat. Now I want to point out this is a continuum. Because sometimes, let's say you're a runner, onset of activity, you're doing great, you keep running, you get into this energy system, and maybe you even get past here. But what if you become fatigued? It's possible for you to backtrack a little bit. Maybe you don't have as much oxygen available, you're a little bit more out of breath, and you're not able in that moment of running to bring enough oxygen to the muscles, so you may have to backtrack to use some anaerobic means. But then once you've brought in more oxygen and that oxygen has gotten down to your muscles, then you can go back down to using this one because now you have enough oxygen. So the point is, we can shift between these. Even though at first, from the immediate onset, we always go in this way. At the immediate onset of activity, from time 0, you're always going to progress from the top to the bottom here. But as exercise continues, you may actually fluctuate and go back to burning more glycogen for a period of time, and that's absolutely fine. All right. So what affects our movement through this spectrum? So this spectrum I was just talking about. What affects our movement through it? You already know a lot of this. So a lot of it is a review. If we have a high intensity, we're going to be at the lower end of the spectrum. At a really high intensity, you're going to be staying at a high intensity, you're going to be staying up here at a high intensity. At a longer duration, as duration goes up, at a longer duration, you're going to be down here. So what we're saying is, and I know I have so much written on this screen, boy, it's going to make us look so smart, isn't it? When you're here, it tends to be high intensity exercise that doesn't last very long. Okay? Versus when you're here, it tends to be at a lower intensity. You're not going quite as hard, but it's lasting longer. That about sums it up, really. The last thing I want to add here is fitness. The better fit you are, the more in shape, you will more quickly move into the aerobic metabolism means. Oh. And that's a good thing. So the more fit you are, one adaptation to training, the more fit you are, the more quickly you're going to get to our aerobic means down here. And that's a good thing, because that's going to give us the most energy per gram. The rest here is all extra, but I would review those. Okay, we're almost done here. A couple odds and ends. What regulates our movement through this? How do our muscles know where to go? And we're going to keep it pretty simple. How do our muscles know? Well, there's intracellular chemicals, otherwise known as factors. Actually, I'm not going to have you know that. I'm going to focus on these two. As is the case with most of our body system, we rely on our nervous system and our endocrine system. The nervous system communicates through nerve impulses, so we can send nerve impulses to our muscles from the brain, and the endocrine system uses hormones. We rely on these two. So how do our muscles know what to do? How do they know when oxygen is available and they can switch into the aerobic metabolism? Because of nerve impulses and hormones. Let's keep it that simple. Nerve impulses and hormones. You don't need to know these chemical factors. They're there. You don't need to know them. We're going to talk about this more later. I don't think we really need to talk about it much now. So you can just leave it simple. Our muscles, how do they know what fuels to use and what chemical reactions to use? Because of nerve impulses and because of hormones. You don't need to know these specific hormones. I know some of them are starred, but you don't need to know them. Okay, couple odds and ends. And then we are done, folks, for this chapter. What are the causes of fatigue? This is a really interesting topic, and I believe that in the next couple decades, we're going to be learning much more about it. basically, if we want to keep it really simple, fatigue occurs when you don't have enough ATP. So for whatever reason, your muscles, even though they're crying out for fuel, they're crying out for ATP, you become fatigued during exercise when you just don't have enough ATP. Now, how that happens, there's a lot up for debate. There could be some kind of disruption to the energy supply. And I'll be honest with you, that's what we used to think was really the only answer. Well, if the muscles don't have fuel, it must be because of an inability to produce ATP. But there's been research coming out that shows, we have so much glycogen in our muscles. You have enough glycogen to run 20 miles. But if I ask each of you to run 20 miles, you may not be able to do it naturally. And it's not that you don't have enough potential energy there. You have glycogen. It's just that you're not able to utilize it in a certain way. It could be an accumulation of something. So we know, for example, that an accumulation of lactic acid can turn the blood acidic and can interfere with our energy metabolism. Yet, when we do studies and we look at fatigue levels in runners and at the same time measure their lactic acid levels, there is not always a direct correlation. So it's not always that you're more fatigued when you have more lactic acid. We know lactic acid plays a role, but it may not be that easy. It could we could be fatigued potentially because of a problem with the muscle. Maybe not enough calcium, because that's something that we need in that process. But it's really unclear, to be honest with you. I want to mention briefly lactic acid. Bear with me because we're almost done here. And I want to be very particular. Lactic acid builds up during prolonged anaerobic metabolism. So when you're utilizing the intramuscular high energy phosphate and the anaerobic metabolism, when you stay there for a long time, you're going to accumulate lactic acid. Now, we always have lactic acid. Lactic acid is a natural byproduct. It's only a problem when that lactic acid accumulates excessively. And it only accumulates excessively when we spend too long in the anaerobic metabolism. And the only reason that you wouldn't be able to move from the anaerobic metabolism to the aerobic metabolism, the only reason that you wouldn't be able to do that is not having oxygen, because that's the only real difference. In order to move from the anaerobic means to the aerobic means, you just need oxygen. But if I don't have enough oxygen, then I can't move to the aerobic means, and I'm forced to stay here. And when your muscles are forced to stay in the anaerobic metabolism for a long time, they will produce excessive and accumulate excessive lactic acid. This could occur during prolonged high-intensity exercise. I always think about the 400-meter run. So I would give the example of the 400-meter run. I was never fast enough to be in that, but 400 meters, 400 meters is one lap around the track, right? Yeah, because a mile is 1,600 meters. So that one lap around the track, that's a hard event because it's too long to be a full sprint for the whole way. 100 meters, you can just sprint all out, right? But the 400 meters, it's like too long to be a full sprint, but it's not long enough where you can just kind of get into a rhythm and have it be aerobic. So that's an example where I'm really pushing the limits, where I'm trying to sprint for as long as I can, and I may stay in that prolonged anaerobic metabolism, or You could also accumulate lactic acid during an endurance event where you did go from the anaerobic metabolism, where you initially successfully went from anaerobic metabolism to aerobic, and you're feeling great, but by mile 20 of the marathon, you start to have a lack of oxygen. You're fatigued, you can't keep up with oxygen delivery, so you actually may work your way back. So you may also consider lactic acid accumulation when you've already been through aerobic, but you reach a point in an endurance event where you don't have enough oxygen to the muscles and you have to work backwards. And then you end up spending too long in the anaerobic metabolism. How to limit? Train well. Be in shape, folks. Another thing is to progress slowly. So don't go, the example's a weekend warrior. Oh, I'm fine. I'm going to go run 10 miles today. Well, if you haven't run in a while, don't do that. Progress slowly. Okay, I do want to give some credit to my man, Eliud Kipchoge. I talked about the wonder of Usain Bolt. Let's talk about the wonder of another endurance athlete. If you missed it, not long ago, Eliud Kipchoge ran a full marathon, 26.2 miles in 1 hour, 59 minutes, and 40.2 seconds. That is crazy. Because you know what? That is an average per minute mile pace. He ran each mile at 4 minutes and 34 seconds. Think about how fast that is. I know that my fastest mile time is about 6 minutes, and I felt like I was sprinting. So imagine running a 34-minute mile over and over again. Now, of course, this is not going to be an official world record because, as you can see in the bottom picture, he had runners around him that actually kept coming in and out in shifts. That was to help him pace, so he would pace appropriately, and also to maybe shield him a little bit from some of the wind. Also, there was that car in front of him with the green light, helping him to stay on the track, the green light, to make sure that he was running the shortest possible distance on that route. But absolutely amazing. This is some extra information, but you know what? I think we've covered enough. So I'm not going to say anything. The only thing that I said, changed my mind actually, that's the beauty of being the teacher, is I do want to point out what I said. We have so much glycogen in our skeletal muscles and liver. So people usually have enough glycogen. People will say that the body stores enough glycogen for 20-mile run. Can you believe that? Woo! So even though we have, so I'd like you to know that we actually have so much glycogen storage, but it's just not as easy as only having the fuel storage. You also have to have your muscles able to use it. So as I just said, fatigue during a long-term exercise is not due to a lack of fuel, because we have tons of fuel. There's something else. I'm just going to leave it at that. I think we're going to learn a lot more about this in the coming years. What we've learned is that during a long endurance exercise, fatigue doesn't happen because there's not enough fuel available. You got tons of muscle glycogen. It's just that we're not quite able to use it. All right. This is our last slide, and I would like you to know some of these. Through exercise training, there are some metabolic adaptations. We know that when you train, you're going to get more fit. You're going to be able to do better. But what's actually happening physiologically? Let me give you some examples. In a resistance exercise, like a sprint or weightlifting, when you train more, you can actually increase the number of type 2 muscle fibers you activate. That is a metabolic adaptation. If you lift weights over a period of time, the longer you lift weights and train, the better able you are to activate type 2 muscle fibers, which are the muscle fibers for that fast twitch. The better that you train with endurance, you actually increase your number of mitochondria and their size. The more endurance training you do, the bigger your mitochondria. And if you have a bigger mitochondria, you can do more energy metabolism. You can create more ATP. Another thing with endurance, the better off you train, you'll have less lactic acid accumulating. So of the many metabolic adaptations, I'm only asking you to know these. All right, well done, everyone. We'll keep on going with the next one.